So you want to learn about move semantics? You've come to the right place. So what's all this about anyway? To learn move semantics, let's show what the problem is in the first place. Let's suppose we have a class named widget with a public constructor which doesn't do much, and a private field, let's say int pointer. Okay, now let's suppose this widget wants to create an array of ints. Let's define our bounds, because we hate magic constants and you should hate it too. Elements, whatever, a big number. Yeah, like that. Beautiful. So we have our memory, we need to destroy it in the destructor. Delete, delete, delete. Beautiful. Does it compile? Of course it compiles, why not? Okay, so we have this class and we see it's missing something. It's missing a copy constructor and copy assignment operator. Well, let's make one or two. Widget, other, oh yeah. Let's allocate this memory again. And let's copy. Copy. Pointer, other, pointer, size of int times num elements. Okay, this is a really heavy copy constructor. It copies a lot of memory. We don't like copying a lot of memory. Let's see about our operator. We get other, a little sanity check. This, and again let's copy all this shit. Turn this. Yeah, a really heavy copy operator. We don't like it. So why do we need this stuff anyway? Well, if the widget gets copied anywhere, well, we don't want a double delete or anything like that. That's what exactly is going to happen when we leave the implicitly defined copy constructor and copy assignment operator present. So we need our own. Okay, now let's suppose we have a vector of widgets. Let's say it has 5 default constructed widgets, whatever. So what now? Let's suppose we want to sort that vector. But first, in order to sort it, we need some kind of notion of equivalence. In C++, the notion of equivalence is done by the less operator. Let's make one. Actually, this is pretty irrelevant to move semantics, what I'm writing here, but for the sake of this lesson, let's just write it because, you know, I want to sort this shit. Return. Let's just compare the pointers or whatever. If you're wondering why I'm using less for this, well, that's a topic for another lesson. Just assume it's needed in general. Okay, so we have our equivalence, more or less, and let's sort stuff. Begin. And so let's see what really happens. Some logging might come in handy. Copy constructor and line, and of course a typo because why not. And our copy operator. Yeah, let's run this stuff. No warnings. Very good. Yeah, a lot of copies. So what really happens? Sort to sort all this stuff uses swapping to swap elements around. And how does such swap work? Well, if you remember, swapping is actually making a temporary object which is assigned all the values of object 1, then object 1 is assigned to object B, and object B is assigned to this temporary, so we have pretty much 3 assignments, or a construction and assignment and 2 assignments, or whatever the implementation is. In fact, we are just dealing with 3 copies. Do we need them? Not really. We just want to swap elements around. Why the hell do we need to copy all this stuff? Why the hell do we need to allocate memory, copy all this memory, then deallocate memory from these temporary objects in the swapping algorithm? We don't need all of this. That's why people thought, hey, let's make something that will just take the stuff out of one object and clear the data in the object so it doesn't free the stuff that we've taken from them. That's exactly what a move is. It's a new addition to C++, it was added C++ 11. Now, let's see how it works in practice, and let's see how to make it work. But first, we need to dig into some theory. We need to know what are rvalue references, another new addition to the standard. As you see, without rvalue references, we couldn't have moves. What is an rvalue reference? Well, let's delve into some history. C++ traditionally had 2 types of values, an L value and an R value. An L value, in short, is anything which can have its address taken. So for example, if I write type 6, the I here is an L value. How do I know that? Yes, I can do that. It works. Of course it works. Because I is an L value. Now, what are R values? R values are pretty much the opposite. These are things which cannot have their address taken. For example, temporary objects. Let's see. Suppose we have a function f which returns some integer. This is of course a temporary object that is being returned. So let's try to take its address. You already see the compiler is screaming. It's an error. It won't compile. And what a nice error we have. This little bugger here requires an L value, while we are giving him an R value. Okay. So, what next? A certain problem arose. How do we distinguish an L value from an R value? Suppose we have a function, and this function has one overload which takes an L value, and one overload which wishes to take an R value. Historically, how would we do that? Well, that was one way. Use a non-const reference, or use a const reference. So, how does it work? When you have a non-const reference, we can only bind this reference to an L value. So if I have something like this, an L value, and I can call fi, this will call this f, which takes a non-const reference. Now, suppose we'll do something like that. 7 is a temporary object, therefore it's an R value. So it will get caught in this overload. Okay, so what's the problem? The problem here is this is a const. And when we do something like that, const in 8, Now we have a problem because this L value gets caught in this overload. So in general, can we distinguish an R value from L value? Historically, of course. No. That in general doesn't work. So people, smart people in the standardization community thought, let's create a reference to a true temporary object which is additionally mutable. So they created something called an R value reference to ampersands. Now, why the hell did I delete it? Whatever. Now, if I have something like that, well, I can already see it calls this overload. Okay. If I call it with an R value, it calls this overload. Okay. So what about this case? This case is a bit problematic because you see in the previous example a const int ref would catch this value. Right now we have non-const reference here, so we cannot call f with a non-const reference, and also we cannot call f with an R value reference because this is an L value. Now, why is that knowledge handy? You see, if we have an object, a temporary object, we can make a function overload which will take that object. And since it's mutable, it's non-const, we can take the insides of this temporary objects, then you'll have all the memory this temporary object possessed, and it's our own. It's pretty simple. Let's see in practice how this works. In addition to copy constructor and copy assignment operator, we now have something called move constructor and move assignment operator. Nice stuff. Let's see. Here we have an R value reference, which means the other is probably, we'll talk about it later, is probably a temporary value. And since it's a temporary value, why the hell do we need to copy its memory? Why the hell do we need to allocate this array of ins? Why the hell do we need to do this memcopy when we can simply take its memory pointer like that and clear it so the other object doesn't delete this stuff while we would delete it later, and everything's fine. So what happened here is essentially a move. We moved the ownership of this memory here, and we cleared the ownership in the other objects. Pretty fine, pretty nice. Now let's see about the operator. It's pretty similar. Of course, a sanity check, some logging. I'm gonna add some logging here too, by the way. Constructor, end line, because I like end lines. Pointer, under, pointer, under, pointer, blah blah blah. Null pointer, a lot of pointers, and return this. Voila! So we have our move constructor and move assignment operator. So what has changed in runtime? Let's see. Compile, 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 run. Ha! Now you see, we have no copies anywhere. all we have are moves. We are moving memory around. We are not allocating any ints. We are not copying memory. We are not deallocating them later. Everything is super fast. But how does swap in a sorting algorithm knows it can move the object, this temporary object that it uses to swap values around? You see, move is very smart. If an object can be moved, it will be moved. If it can't be moved, move is implicitly converted to a copy. But there's another question you're probably thinking about. If not, you should be thinking about it. When we swap, we are really creating a temporary object, but it's not actually a temporary value per se. It's logically temporary because we're getting rid of it right away, but it's really an L value. So how the hell can we move something into or out of an L value? That is pretty easy. It's pretty easy because all you have to do is cast this L value to an R value reference. And therefore, the overload, which will be called later, will choose the function which takes an R value reference. In our case, for example, a move assignment operator rather than a copy assignment operator. In the standard library, we have a helper function for that, called move. Obvious, right? Let's see how this works. Suppose we have a string with a typo S, A, B, C. Now suppose we have a string 2 which would like to take the contents of S, not copy, take. So we just call move from S. That's it. That's all the magic. Move casts S to an R value reference, which in turn is passed to S2, appropriate overload is being called, and S2 takes the contents of S and clears what S takes inside. Small note, it doesn't actually have to clear it. The standard says that if an object gets its data taken, it's supposed to be left with a valid state. What constitutes valid? It's up to that object. It doesn't necessarily mean it's empty, but it must be valid. All the preconditions must be kept. So, okay. That's essentially how swap moves things around, using standard move. So you see, now we are sorting this vector of widgets without any copies, without any unnecessary allocations, without any unnecessary deallocation, and everything is super fast. Small quirks, small caveats, small things about move semantics that you should know. First, you may know, well, you should know, if not, then you will know in a second. Copy constructor and copy assignment operator are usually implicitly defined by the compiler. If a class is copyable, if it can be copied, its contents, its parent classes allow it to be copied, then a copy constructor and copy assignment operator will be implicitly defined and will simply copy the contents of inner members to another object. Move constructor and move assignment operator can also be implicitly defined by the compiler, but not always. Unlike copy constructor and copy assignment operator, the rules are more strict here. If you declare your own copy constructor, copy assignment operator, or even your own destructor, then move constructor, really repeating all these words, the move constructor and move assignment operator will not be implicitly defined by the compiler. No. So the rule is, if you declare your own copy, your own destructor, operator, constructors, etc., you should also define, if it's applicable, your own move constructor and move assignment operator. This is called the rule of 5. If you declare any of the special functions, declare them all. Of course, if applicable. Second, not every type is movable. You see, primitive data, plain old data, isn't really movable. Moves in general work well when we're dealing with dynamic memory management, when we are allocating or deallocating memory, because we can just move some pointer around, right? But what if we had something like this? An int. Simple. How the hell can we move a simple int? We can't. We can just copy this stuff, so it would work like this. And so on, and copy constructor and all these operators, etc., etc. You see, you cannot move an int, you just can copy it. It's a plain old data, it has no dynamic memory, you just copy these few bytes and that's all. So bear in mind, even if something has the move constructor or move assignment operator and you call and move on it, it doesn't mean the internal data will be moved. It might as well be copied. You'll never know. But it's always better to move if you want to move, because in general we'll probably move stuff around. And third, it's pretty much the opposite of the previous thing. Not every movable type is copyable. Let's suppose you have some class which owns data, right? Let's say our widget owns int and doesn't want to share the value of the int. This is his. He doesn't want to share it with anyone. That means if we're moving, we can move the int to a new owner, because we are giving away this ownership, but someone is taking this ownership from us, but we don't want to copy it. So we might as well just comment out copy constructor, copy assignment operator. And now we have a class which is movable, but which is not copyable. An example of such class is a standard unique pointer. It owns the underlying pointer and doesn't really want to share it with anyone else, but it's willing to give it away to another unique pointer. If you'd like to see more lessons, please click on the button below to subscribe. Stay tuned for more episodes and code well.